The 2022 Nobel Prize in Physics recognized a series of experiments that did what many once thought impossible. They provided a physical answer to a question that remained purely theoretical for nearly a century. One of those laureates was French physicist Alain Aspect. In the early 1980s, Aspect took on the challenge of designing a machine that could finally put Albert Einstein's deepest doubts about quantum mechanics to a rigorous laboratory test. The conflict began in 1935 with a paradox proposed by Einstein and his colleagues. They were troubled by quantum entanglement, a state where two separated particles seem so deeply linked that measuring one instantly reveals the condition of the other, no matter the distance between them. Einstein argued that these particles didn't need instantaneous communication. Instead, he proposed they held local hidden variables, pre-programmed instructions set from the moment they were created. Imagine a pair of gloves placed in two separate boxes. If you open your box and find a right-handed glove, you immediately know the other box contains a left-handed glove. The state was determined before the boxes were ever mailed. This created a 30-year philosophical stalemate. Quantum mechanics claimed the particles had no definite state until the moment of measurement, while classical physics insisted on Einstein's hidden instructions. Because no one could see what the particles were doing between the source and the detector, the nature of reality remained a matter of opinion. The path toward a resolution appeared in 1964, when physicist John Bell published a mathematical theorem that turned this philosophical debate into a testable hypothesis. Bell realized that if Einstein's hidden variables were real, there was a limit to how often the measurements of two particles could correlate. He calculated a hard mathematical ceiling, a specific number classical physics could not cross. Quantum mechanics, however, made a startling prediction. Entangled particles would break that limit, showing a correlation impossible if following preset instructions. Bell had provided the formula, but the scientific world now needed someone to build a physical machine precise enough to see if that ceiling would actually hold. Alain Aspect took up that challenge in the late 1970s. He knew that for his results to be irrefutable, he had to solve a problem that had plagued every previous attempt. Early experiments in the 1970s had a fatal flaw. They used detectors with fixed static angles. The settings were locked in long before the particles ever left their source. This created what scientists call the locality loophole. If the detectors are preset, the machines could theoretically be sharing signals at the speed of light, telling the source how to emit the particles to fake a quantum result. To truly isolate the particles and kill the hidden variable theory, Aspect had to design an experiment that could change its mind faster than light could travel across the room. In his lab at Orsay, Aspect constructed a system that fired 100 entangled photons every single second, creating a stream of quantum data. He positioned his polarizers at opposite ends of the laboratory, placing them exactly 12 meters apart. To prevent any secret communication between the devices, Aspect installed a mechanism that switched the angle of the polarizers while the photons were still in flight. Light takes about 40 nanoseconds to cross that 12-meter gap. Aspect's system executed its switch in just 20 nanoseconds. The measurement was chosen and finalized before any signal from one side could possibly reach the other. The results were staggering. The correlations Aspect measured didn't just nudge past Bell's limit, they violated the inequality by 242 standard deviations. This wasn't a statistical fluke, it was a definitive result. By changing the settings in midair, Aspect proved that the links between entangled particles are real and instantaneous, effectively ending the era of local hidden variables. Even after Aspect's success, some skeptics looked for one final escape for classical physics, the detection loophole. They argued that because standard detectors miss many of the photons fired at them, the data might be skewed. If we only catch a fraction of the particles, how do we know the ones we missed aren't following Einstein's rules? Between the years 2013 and 2015, physicists finally closed this gap by moving the experiment into extreme cryogenic environments. Using superconducting detectors chilled to near absolute zero, they were able to catch nearly 100% of the entangled pairs. By combining these high-efficiency sensors with Aspect's fast-switching methodology, scientists achieved the first loophole-free tests. Every classical explanation for entanglement had been exhausted. This transition from theoretical puzzle to experimental fact changed how we view the information density of the universe. Entanglement is no longer an embarrassment to explain away. It is a technical resource used to build unbreakable quantum cryptography and global quantum networks that transmit data over optical fibers. The 2022 Nobel Prize was more than a tribute to three physicists. It was an acknowledgement that we have moved into a new phase of scientific capability. Alain Aspect brought the most elusive properties of the microscopic world into the laboratory. By confirming that entanglement is a physical reality, he showed that the strange correlations Einstein doubted are actual physical tools, the very components now powering the quantum computer